All right, as part of Unit 2, we have to look at population calculations. And as you read in the first reading assignment, we can utilize a standard exponential growth formula for projecting population sizes. And so this is should be familiar if you've studied exponential growth in another class, or you've looked at exponential decay in radioactive materials. It's essentially a basic formula that gives us the ability to project a population size that is growing exponentially. So if we look at this standard exponential growth equation, we have some important pieces. The original population and on 0 there. Our new population is there. Time, and this is important because we're looking at time in years if we are looking at the growth in years. If we're looking at growth rate in months, then that time has to be put into our month unit, and we'll see that in a second. And then R here, notice it's a little r, so we have the growth rate as a decimal, and if we see a big R, we know that's growth rate as a percentage. So we can use this to calculate and to project population sizes. So our first example here is utilizing our exponential growth rate equation to look at the population of an ant colony. And if we look through the question, we know that it's growing at 2.2% every month. So that should key you into this T. We want to know the population after 1 year and then after 5 years. So what I'd like you to do is work through those calculations. Let's hit pause on the video, and then we will come back and look at those together. So hit pause and work through those two calculations. All right, so if we look at our equation, n equals NO, so our original times our growth rate and our time. And this is a constant. It's the exponential function. It has a basic value of 2.72, and we don't need to get into how that's derived, but we can use that in our calculation. You can also hit the funky E button on your calculator when you are doing this. So if we look at the first example, the growth rate or the growth of the population after a year, we want to know n, and we have our initial population times 10 to the 5th, so 175,000, and we're going to multiply that by, we'll go 2.72, and we know R. The growth rate, if you remember, was 2.2%, so 0.022 in a decimal. And then our time is based on the growth rate. So remember, the growth rate was 0.022 or 2.2% per month. And so in this case, our time has to be 12 months. And so when we do that, we should, putting it into the calculator, or you should have gotten an N, or new population of ants, at 227,870. We'll do that, a little dyslexic. 872 ants. All right, so the critical thing here is doing that in months because our growth rate was in percentage per month. So if we scroll up, we can look at, we'll move that up so we can go into our second calculation, which is looking at over 5 years. So we would set it up. N equals 1.75 times 10 to the fifth. Ants times our 2.72, and then to the exponent of 0.022, and then we have to multiply it not by 12 months as we did there, but by 60 months, which would give us a 5-year time span. And when we multiply this out, you should get something close to 655,099 ants. Something around there. I think when I did the calculations, I utilized the E button on the calculator, so you might have something slightly off, but you should be close. All right, so that's how we utilize the projecting population equation using the standard exponential growth equation. All right, the second example is utilizing a derivation of that first equation and isolating our R value, or in this case, the growth rate. So here we have 1 over t, so remember t is based on the R value, and then we have our n, which is the final population, and NO, which is our initial population. So here we're going to take this example of mountain gorillas. So in 2006, we know the population was 302. 2010, 4 years later, we have 480 population or mountain gorillas. And what was the growth rate? So we're going to use that information to find our R. So what I'd like you to do is hit pause at this point, work through the calculation, and then in the next slide, I will go through your explanation. All right, so we use our equation to calculate R. So R equals 1 over t, and t equals time, times the natural log of our initial population, or our final population, NF, over our initial, N0. So if we substitute what we know, R is going to equal 1 over 4, because we have a 4-year period. And then we'll do the natural log of 480 divided by 302. And when we put that into our calculator, we should end up with a R value of 0.11. And so that essentially says that we have a R value of 0.11. Remember, that's growth rate as a decimal. If we wanted to look at it as a percentage, our big R, we would just multiply that by 100. And our big R, our growth rate in percentage, would be 11% per year. And so we would see the gorilla population increasing at 11% per year. All right, the last example is looking at how long it takes for a population to increase at a certain percentage. And so here we have an example looking at rats in New York City. And if you've ever been in New York City in the subways or near a trash pile, you will know that New York City has a lot of rats. And so here we're looking at the estimation that there are 6 rats for every single person in New York City. New York City has a population of 8.3 million people. And if rats produce at a rate of 4.2% annually, when will the population of rats reach 200 million? So we got a couple of little curveballs in this problem. So take that little tidbit and see if you can set up your projecting time equation based on the information given, and I will be back. So press pause, work through the problem, and then our next slide will go through the problem and get you a solution. All right, so press pause. All right, so if we take our equation, so time equals 1 over our growth rate times the natural log of our population final over our population initial. And so in order to start putting in our information, we have to think about what our R is and our population initial in this case. So our R, we said 4.2% annually. That has to be transferred into a decimal, so we move the decimal place 0.042, and so that'll give us our R value, or the growth rate, in a decimal. Our N initial is a little bit more convoluted. We knew that there were 8.3 times 10 to the 6. 1, 2, 3 people, so 8.3 million, and we know that there are 8 rats, so 1 person equals 8 or 6 rats. I apologize. And so we come up with a total rat population of 4.9 times 98 times 10 to the 7th rats. So again, we take the population of New York, multiply it by the number of rats per person, 6 rats per person, and we get a total of 4.98 times 10 to the 7th rats, or 49 million rats currently, or in 2011. So let's take our new values and substitute them into our equation. So the time would be 1 over 0.042 times the natural log of our final population, 200 million, 0.0 times 10 to the 8th, over our initial, and 0, 4.98 times 10 to the 7th. And so when we do that and we substitute that in, and we look at a final answer, we should get a number that is very close to 33 years. And so it's going to take 33 years for the population to increase with that annual growth rate of 4.2%. So we originally in the problem wanted to know when this will occur. So we started in 2011. We have to add 33 years, and you should get 2044. If the growth rate stays the same, it will take 33 years for the population of rats in New York City to reach 2.0 times 10 to the 8th, or 200 million rats. All right, example 4 uses what we call the rule of 70. And the rule of 70 is simply stated that the doubling time, the amount of time it takes for a population to double in size, equals 70 divided by big R. And remember, big R equals our growth rate in a percentage. So if we take the doubling time equation, rule of 70 equation, and substitute, we get doubling time equals 70 divided by 3.5, and so 70 divided by 3.5 gives us 20. So in this example, it would take 20 years for a population to double that has a growth rate of 3.5%.